let's look at a function that actually will do stochastic gradient descent for us. It's got the same stuff as before. We pass in our initial guess of our parameters. Here it's the intercept and slope, our initial learning rate, our learning rate decay power. But there's this new thing called mini batch size. Oops, sorry about that, mini batch size, and that's how big of a sample to take from the data set each time. When stochastic gradient was first invented, people thought of using a mini batch size of 1. Just take a single data point and use that to evaluate the gradient and take a step. These days people tend to use mini batch sizes that are bigger than 1, often powers of 2 some people like to use. In some cases you might be reading an entire block of data off a hard drive or off a SSD, and that might be 64 megabytes, which seems maybe big, but if you've got a data set that's in the terabytes, then 64 megabytes feels like a mini batch. So that's the new parameter we're setting here, and that will help determine how quickly we get to the optimum. And it's not something that affects our ultimate model. We can take this model and use it somewhere without saying what the mini batch size was. So that is a hyperparameter. So here we're just setting up some room to store our results. We wouldn't always do that in real life, but here, since we're studying how this works, we want to see how each step went. We're saying here's how many epochs I've done so far, starting that at 0. And location here will say, where does my mini batch start? And then I'll go however many data points are in a mini batch step. And then the next one I'll do over here, and then over here, and then over here. So I'm doing something for pedagogical purposes in this file that you probably wouldn't do in real life. And that's, I'm just saying, here's my first mini batch, here's my second, here's my third, if I have a long array of data. Really, you should be taking random samples from it. If you randomize the order, then taking it in chunks is a random sample. But then the question is, should you do it in the same chunks in the same order next time? Again, for pedagogical purposes, we'll do it in the same pattern every time, and we'll see how that goes. And let's see, I'm taking a little shortcut here. You can read about that later. So we're just saying take data from wherever our current location is to a location plus the mini batch size. That's our sample. And then we're updating where our location is to start at the next place. And we're saying if that runs off the end of the data, set the location back to 0 and say, hey, we've finished one more epoch. Then we pass the sample data, the stuff from the mini batch, to our regression and to get the gradient. We store stuff. Notice that what we're saving there for the function value is on the data sample, not on the entire data set. Again, for pedagogical reasons, we want to study how this is going compared to full batch gradient descent, which means what we already learned is gradient descent, evaluating the entire objective function. So here we're taking this extra step of computing the objective function on the entire data set. Usually when you're using stochastic gradient descent, you wouldn't do that because the whole purpose is to avoid doing this because that slows you down. But here we're studying it, so it's okay. And then we're doing just the same update as before, our initial learning rate times some kind of learning decay times the negative gradient. Add that to my current coefficients to get my new coefficients. And here's an interesting story. Should I base my learning rate decay on how many mini batches I've processed or how many epochs I've seen? So we'll come back to that. Some people say one way. Andrew Ng is a famous machine learning scientist and teacher, and one of his videos says use the epoch number here, and we'll go back and see what are the trade-offs there. Or maybe there's something to discover that's not a trade-off. All right, so here we're going to randomize the order of the data. We chose, again, just a random seed. You can choose any number you want, like your area code, the last 4 digits of your dog's phone number, whatever you want. But just record it here like we're doing so we can come back later and change it and see how things vary. And sometimes we want to do a bunch of trials and have a system for what the seeds are, like increase it by 1 for each trial. So here we're saying give me a random permutation of the numbers 1 through n, and then use that permutation to grab data out of the x and y arrays in that random ordering. So here's what the original x data values were. You can see it was sorted by x value because we just generated x values like from 2 to 8 by steps of 0.01. And just to check that our data did get shuffled, looks reasonable there. Just to check that everything's going okay, we're computing the least squares, slope, and intercept using other methods for our original data and the shuffled data. So that looks good, everything matches. We're going to just use whatever initial learning rate and learning rate decay we were using for the non-stochastic gradient above. And here's our choice of what kind of mini batch size do we want. I'm going to use mini batches of size 50 to start with. Remember, we have 600 points in the data set. We could say one mini batch per epoch. That would be just use the entire data set. So that would turn stochastic gradient descent into just plain gradient descent. That's a good debugging tool to see, is SGD working how I expect? Well, let's make it run the same way that gradient descent works, and if we don't see the same numbers, then we know we have a bug somewhere. All right, I'm going to just say run 400 epochs. Usually on larger data sets, you would probably not have time to run 400 epochs. And then figuring out, well, then how big is each mini batch if I have this many mini batches per epoch. Here I'm not setting a seed before we call the SGD, because the SGD, again, for pedagogical purposes, is just taking stuff in exact order rather than doing the scrambling itself. But in a lot of cases, especially if you're using prepackaged tools, you would set a random seed before you call the SGD so you can reproduce that. So let's see what it gives us. That was using the old learning rate decay. So here's what gradient descent, full batch gradient descent gave us. Here's what the stochastic gradient descent gave us. And it gave us a final value after 400 epochs of 0.2298, when the true optimal is 0.226, so getting pretty close. Let's take a look at the coefficients it gave at the end. The true best coefficients were like 0.77 and 0.5 something, so looking pretty good. Let's just see how many steps did we take, 20,000. And then let's see what the path is of the coefficients that it discovered. So before we show this graph, take a second, ask yourself, what do you think this is going to look like? Remember what it looked like for plain SGD, plain gradient descent full batch. Here's what it looked like. And here's our graph now. And the yellow is laying the plain full batch gradient descent over the blue curve. That's our stochastic gradient. And here I've marked each epoch with a black dot. So what do you see going on in this graph? And here every red square, every red plus is however many mini batches per epoch we're already doing. So in some sense, the red dots and the red pluses and the black dots should be roughly comparable. So I'm seeing that, yeah, it's converging to basically the same spot. It's kind of interesting that at each epoch we're up here rather than along the central path. Central path isn't a technical term here, but it is in a later, much later in our course. We would tend to just use an integer number of epochs, and so here we're seeing that if I did that, my answers would be systematically too high on one coefficient and possibly too high on the other. You might ask, how might this graph look if we change any of the parameters, hyperparameters? Let's also look at how the objective function changed as we did our iterations. Here the red curve is plain gradient descent full batch. The blue with the black dots is stochastic gradient and showing the objective function value at every epoch. So, it's pretty good, 10 to the minus 3. Here I'm subtracting the true optimal MSE. So ultimately we would hope these go to 0, and these basically do. So this is kind of bouncing around a lot in a pretty good range. We could also look at how does the the slope coefficient that we're trying to estimate, how does that change as we do more and more iterations? It seems to be kind of bouncing around the true optimum value that we've converged to here with full batch gradient descent. And then how about the intercept? Let's see, that was the slope coefficients. I think I have this. Oh, so this is a zoom in on the slope coefficients. So picking like this range here, what do we see? It's basically doing the same thing over and over again and taking the same size steps. And then let's look at the intercept coefficients. That seems to be tracking along pretty well with our full batch gradient descent. All right, so in the next video, we'll investigate more stuff.